Okay, everybody. So what we are looking at today is tangent. So far we've focused our time on looking at sine and cosine. We've had a look at the sine and cosine graph. We've solved equations using sine and cosine. So we're now going to extend our understanding through tangent. The idea is that we will cover both sketching tan functions and solving tan equations within this hour and a half. We do have tomorrow's lesson as a backup if we don't quite make it. So we'll see how we go. So I'm just going to zoom out now so you can see where we're headed. I'm going to start off by just having a quick look at how we define tan. Remembering that trig ratio started as a right angle triangle concept, and they were the ratios of two different sides. So we had sine as being opposite over hypotenuse, cosine being adjacent over hypotenuse, and of course tan is according to those letters there. Declan, start us off. Yeah, and according to those letters there? Yeah, B over A. Very good. So we've got tan theta is as equaling B over A. Now, C is the hypotenuse. I just want to show that according to right angle trigonometry only, if I multiply top and bottom by 1 over C, I know that's pretty small on your screen, but I hope you can see that. So I'm multiplying by 1 over C. And I'm multiplying the top and bottom of that fraction by 1 over C. This is an equivalent fraction. So I get B over C over A over C, okay? B over C we've defined as sine theta, and A over C is cos theta. So purely from a right angled trigonometry perspective, we've got tan theta equals sine theta over cosine theta, just from the right angled trig work. Is that okay so far? So we can see that that relationship is consistent, because what we said in the unit circle, I'm up to slide 3 now, is that in a unit circle, we have a line of length 1. The coordinates of the end of that line are sine theta, cos theta, wrong way around, beg your pardon. Cos theta, sine theta for an angle theta that the line makes with the x-axis, like so. And then we said, if you remember, that we would define tan, and you can see now this is consistent with the right angle trig work. We define tan as being sine theta over cos theta. Is that okay so far? This is just refresher work to make sure that you're sort of okay with what we've been doing up until now. Any questions? Okay. And I don't know if you remember, I mentioned this in passing, but it's kind of going to be the linchpin of what we do next. Given that this is a line, a straight line that starts at the origin and goes forward 1 unit, but technically, you know, I could extend that line forever in both directions if you like. We can sort of conclude that tan theta is effectively the gradient of that particular line. So in other words, the family of straight lines that pass through the origin, okay, not above or below, but pass through the origin, that make an angle of theta from the x-axis, the positive x-axis, then the gradient of that line would be tan theta. Rise over run. Sine theta being the y-coordinate, and cosine is the x-coordinate. Goodly doodly? Okay, so what I just wanted to point out is that we've talked about how we've got a cast diagram. So I'm looking at slide 4 now. And we know that for tan, we've got tan being positive here, tan being positive in the third quadrant, it's negative here and negative here. And excuse me, just quickly, if I just use red for positive and blue for negative, if I draw an angle in the first quadrant, the gradient is positive because it's going left to right, it's going upwards. And if I draw, say, I'll do it at a different angle just so it's quite pronounced. Oops. Come on, Richard, use your ruler. Now it's gone purple, that's weird. Try that again. Okay, and if I have an angle here, oh my gosh. Like so, I won't label this one because it might get a bit confusing. Then the gradient is positive here as well. It's a positive gradient here, or it's a positive gradient here, depending on that line. So either way, you can see that according to our knowledge of gradient, that we have a positive line here, and we have a positive gradient here and a positive gradient here. And similarly, if I look at where tan is supposed to be negative, that correlates as well. So I'll just draw them. They won't be nice and straight. So if I draw a couple of angles that would be in the second quadrant or the fourth quadrant, that's confusing. You can see why I want to video it. You can see that the gradient going left to right is negative because it's going downways. So that kind of correlates to the cast diagram as well. Okay, so if you think of tan as being the gradient of that line, it might make a bit of make a bit more sense of the understanding as we progress. Any questions? Good so far? Alrighty. So let's have a look at what the graph would look like of tangent. I'll just hide that message so we don't lose that bit of screen space. Okay, so first of all, let's just see that here is 0 degrees or 2 pi at a full rotation. Here is pi on 2. Here is pi, and here is 3 pi on 2, or 270 degrees. Okay, so that's where our angles are. So what I thought we might, sorry, question? That's cool. What I thought we might do is we might just start constructing the graph in a little bit of detail as we go along. So first of all, excuse me, sorry. First of all, let's have a look at the zeros. If you have a look at the graph from the cast diagram, if I say, for example, take an angle which is really close to the x-axis like so, when I bring that angle down to 0, what's happening to tan? Well, at 0, so 0 degrees or 0 radians, at 0, tan of 0 is going to be sine of 0 over cos of 0 because of that special relationship, right? Sine of 0 is 0. You can see that from the unit circle I've got here. Okay, there's no that's what 0 would look like. There is no y movement. There's only x movement. So cos theta would be 1. Okay, so tan of 0 equals 0 over 1, which is equal to 0. So at 0, tan 0 equals 0. Okay, does that make sense so far? So that means, according to the graph, which I'm looking at it in slide 8, I've got effectively a coordinate of 0, 0 there. So when the angle is 0, tan is 0. Also at 2 pi, we're going to have a 0 as well. Same reason. At 2 pi, we've done a full rotation. So the cosine of 0 is 1. The tan of 0, sine of 0 is 0. So 0 divided by 1 is 0. On the other side, we've got the same deal, right? So if I go 1 unit backwards here, I've got what angle? Eliza? Sorry? Yeah, 180 degrees, aka pi. Good. So we've got an angle of pi. This is 1 unit out, so it's now -1. So at pi degrees, pi or 180 degrees, the tan of pi is going to be equal to sine pi over cos pi. Sine pi again is 0. Cos pi is -1. But again, 0 divided by anything is just 0. And so we have 0. So right in between 0 and 2 pi, we've got pi. Excuse me, sorry. And that is also a 0 on our graph. So we've got, so when I say 0, by the way, I'm talking about an x-intercept. So I've got an x-intercept there, we've got an x-intercept there, and we've got an x-intercept there. So far, it's going to pass through there. I'll just zoom it up for a second so you can see that. We'll have an x-intercept there when the angle is 0, an x-intercept there when the angle is pi, and then we have an x-intercept here at 2 pi. Okay, just going to give you a moment to have a chat amongst yourselves. The other critical things on the unit circle, I guess, are pi on 2 and 3 pi on 2, so on the y-axis here. So have a chat to the person next to you. What's going to be the value of tan here and here? 0 both? Yeah, beautiful. That second bit is where we're looking at there. You're right, we're dividing by 0. So let me just zoom up here as well so we can sort of see what's going on. So at pi on 2, so when the angle from the x-axis to the unit line is pi on 2, we will have tan pi on 2 equaling sine pi on 2 over cos pi on 2. Sine pi on 2 is 1, cos pi on 2 is 0, and as you correctly said, when we divide by 0, it's undefined, okay? Doesn't exist at that point. Like so. Similarly, down here, we're going to have tan 3 pi on 2 is equal to sine 3 pi on 2 over cos 3 pi on 2, which is equal to -1 over 0, which is going to be undefined again. So we see, excuse me, at those two values, we've got an undefined function. Forgive me, but I can't remember whether we did rational functions in this unit before now or not. Hyperbolic functions, rational functions, I can't remember. Okay, that's fine. So what we have here is, so I'll just zoom out so we can see it all together. What we have here is that at pi on 2, there's a value that is unattainable by the graph. So I'm going to draw in at pi on 2 some more information onto our graph. So at pi on 2 and 3 pi on 2, can you see how that beautifully just splits the graph or the domain up? There, I'm going to have a value which cannot be reached. So we've got at pi on 2, and 3 pi on 2. Oh gosh, that's terrible. This is why I normally draw the lines first and then label it later. There we go. So pi on 2 and 3 or pi on 2, there's a little red bar there to say we cannot actually utilize that value. It is not defined at that point. It is gone from our graph. Okay. All right. So if we haven't done rational graphs or hyperbolic graphs, if I use the word asymptote, is that going to be a new word for people? Asymptote. Yeah.
Something that never touches zero.
Yeah. Hey Seb, wake up. So an asymptote in a function is a value that the graph reaches towards but never actually gets to. Okay, so it heads toward it but never really gets to it, and we'll see it when we look at logarithmic and exponential graphs next unit. Yeah, so just keep that in mind for a second as I move on with this. So these two lines are called asymptotes. So the equation of this asymptote is x equals pi on 2, and the equation of this asymptote is x equals 3 pi on 2. Okay, that's the equation of them. So let's have a look at what's happening in between these asymptotes where the function is well defined, because I hope you would agree that I'll erase this. Oh no, I won't erase, just use the pointer. That between here and here, it is well defined. Then it's undefined here, and then straight after it, it's well defined all the way down to here. It's fine here, all the way down to here. It's fine, but then there's a moment where it can't be defined again, and then after that, it's fine again, and we'll go round and around and around and around, with only being on this axis here where it touches this axis is where it's not defined. Okay, so they're called asymptotes, where it's not defined. So what does it mean though? Let's have a look at what's happening to the gradient of that straight line as we go towards that undefined value. So, excuse me. So, sorry, I'll just use x because that's what a function is normally defined as. As x approaches pi on 2, what's happening to tan of x? Remember that tan of x is in fact the gradient of that straight line. So if I just draw a bunch of them, it's going to look really confusing, but it'll give us a sort of sense of it. So we've got a gradient here. Tan of theta is fairly flat, right? If I go here, tan of theta, the angle is getting higher, and the gradient's getting higher. Go here, it's getting steeper. Go here, it's getting steeper. Go here, it's getting steeper still. So the steepness of the graph is getting more and more and more as we reach towards pi on 2. Okay? So what does that mean? It means that as x approaches pi on 2, the gradient is approaching infinity, getting bigger and bigger is really all that means. Now, from your work in calculus, you should be okay with this idea of approaching. As it approaches, it's getting towards infinity. It's getting bigger and bigger and bigger. So if you think about it, it's kind of, because I'll undo this bit so I won't have this as part of the permanent notes. But what we're really saying is that sine theta is approaching 1, cos theta is approaching 0, but just before 0, we're going to have something like cos theta being 0.000000001, right? Something like that, a really small value. And 1 over a really small value is a massive value. Okay, 1 over a really tiny fraction. So 1 over a millionth is a million. 1 over a trillionth is a trillion, etc. So we're getting bigger and bigger numbers as the angle approaches pi on 2. So what does that mean? So that means that from 0 to pi on 2, we have this kind of approach. Remembering, this is like I'm graphing the gradient effectively. That's like we did in calculus in a way. So it means that from 0 to pi on 2, we have the graph starting off fairly flat, which means tan theta is low, but then it escalates, it skyrockets towards infinity. So we have this kind of thing happening, right? It kind of looks almost exponential in its value. Is that okay? So it's skyrocketing upwards. Now, what's happening in this arena here, between here and here? I'm deliberately skipping these two. This is also a positive gradient because any line I draw here will have a positive slope. So tan is positive, we know that. But again, just after pi, it's a fairly flat graph. I'm just drawing with my pointer so it's not too confuzzling. But as I go now towards 3 pi on 2, again, it's positive, but getting steeper and steeper and steeper and steeper. Okay, so that means that between pi and pi on 2, we've actually got the same thing happening. We've got it going from pi to pi on 2. So at pi, it's 0. And then from pi to 3 pi on 2, it's skyrocketing up as well in exactly the same fashion. I haven't drawn them perfectly the same, but they should be exactly the same fashion. Okay, well, so that's effectively quadrant 1. And this is effectively quadrant 2 there. Let's have a look on the other side. So between here and here, it's starting off steep, but as I go towards pi, it's getting flatter and flatter and flatter as well until it's flattened out here at pi. Or to go in reverse direction, what I'm doing is I'm going from flat to steep backwards, if you like. Okay, so what does that mean? Well, first of all, the gradient is negative here because it's going down ways. Okay, it's going down ways, so the gradient is negative. So it's negative and going from steep down to 0. So what does that look like on the graph? Well, between pi on 2 and pi, we are going to have effectively this happening. Okay, so in other words, at pi on 2, it's coming back from infinity, from a really high gradient, and then it flattens out so that by the time it gets to pi, it's 0. And then after pi, it starts getting steeper again, so it goes up like that. So we've got this sort of thing happening here, and then this, and then this. And lastly, after 3 pi on 2, we're again coming back from infinity here down to a flatter, 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 flatter graph until we get to 2 pi, which is again 0. So from really steep to really flat. Really high value of tan because it's really steep to tan being 0, a 0 gradient. Yep, so that's basically it. And of course, the graph here is negative as well because from left to right, the graph is going down ways. So so it's negative, but going from a really steep negative graph to a really flat where tan is 0. So what does that mean for the graph? It means that we've got this sort of thing happening. Make that a little bit more curvy, like so. Okay, so this between 0 and 2 pi is the tan graph. It's got asymptotes. You can see that the graph approaches the asymptote but never crosses it. Okay, so it approaches this line but never crosses it, and that's what this line sort of shows us here. Between pi on 2 and 3 pi on 2, we can see it's going to approach negative infinity in this quadrant. I haven't written those quadrants in, so that's quadrant 3, and that's quadrant 4. Beg your pardon, I've stuffed that up. That's quadrant 2. That's quadrant 3. And that's quadrant 4. Okay, sorry about that. So quadrant 1, quadrant 2, quadrant 3, quadrant 4. Tan is positive, negative, positive, negative. Okay, so if I went backwards, without belaboring the point too much, if I went down to negative 2 pi, I'd have a similar sort of thing happening, in that if I went backwards, I would have negative pi on 2 here, negative 3 pi on 2 here. But with the same sort of thing, that at negative pi on 2, it would be undefined, and at negative 3 pi on 2, it would be undefined. So if I'm going backwards. So what we end up with in our graph is a very similar looking graph. So we would have pi in the middle. We would have that split, negative pi. We would have negative pi on 2 and negative 3 pi on 2, like so. At pi on 2, we would have that asymptote happening again. At negative 3 pi on 2, the graph is undefined. And so we have this happening. Between 0 and negative pi on 2, that's in here. You can see that the graph is going to be getting steeper and steeper and steeper and backwards, but steeper and steeper and steeper and steeper, heading towards the negative infinity because the gradient is negative here. And so we would end up with that. And then we would have the graph returning. So this is from negative pi on 2 to negative pi. It would be getting from steeper. It would be getting flatter and flatter and flatter and flatter and flatter. That means tan theta is going from infinity back to 0 again. And so we have that. Say that again, sorry, beg your pardon. Wrong side there. Like so. It hits at negative pi, it would be equal to 0. That's talking about here. Same reason as this. And then from here, it's going to be flatter, then racing towards infinity again. So we would have this. And then lastly, we would have from negative 2 pi to negative 3 pi on 2. We would have this happening again here. So you can see that we have a graph. I'm just going to zoom up on that graph now. We have a graph where we have a repeating kind of picture there. Okay, so the picture is this sort of graph here, which is then repeated here, which is then repeated here. And you can imagine if I kept on going to 3 pi and 4 pi and so on, we're going to get that same sort of pattern happening. So that is how the tan graph is constructed across the quadrants. Okay, and just to show you sort of what I mean, here is a little something I prepared earlier. This is just a graph of y equals tan x, just between negative 2 pi and 2 pi. It looks a little bit prettier than the ones I drew. And you can see very much so that we've got up here, we've got tan theta approaching, tan x, sorry, approaching infinity up here. There's the asymptote. And so the graph approaches the asymptote, and then it's undefined at the asymptote. And then on the other side, it starts at negative infinity and then starts going towards 0, etc. So we've got this lovely sort of tangential curve that repeats itself. All right, any questions about that? Hopefully that's making sense to you in terms of why this graph looks like this. You can see that because it goes on forever, talking about an amplitude is a bit pointless, right? So we don't talk about the amplitude of a tan graph because there is no maximum and minimum value for tan. It goes on forever and ever and ever. So what are the critical points in a tan graph then? Okay, so the critical aspects of a tan graph. So if we're looking at transformations, I suppose. So transformations. Okay, so first of all, it should just be pointed out that vertical dilation is not so important for sketching because it goes on forever anyway. I'll show you what I mean. So vertical dilation would be the value I put in front of the tan graph, right? So there's the regular tan graph, the red line. Now I'm going to activate a second graph, y equals tan x. That's why the red line's disappeared now, because it's covered by the green one. So if I put in, say, 3 tan x, you can see that there is a definite stretch. Yeah, the graph is increasing more quickly. But if you could imagine, so although it's important when I'm graphing it like this, there's a definite difference between the two. Could you imagine that if I was sketching it, I couldn't really make that very apparent very easily. So although if you know that there's a number in front of tan, you can sort of exaggerate the curve or the lack of curve. Ultimately, you can't really tell unless you're graphing it against something else. That kind of makes sense. So if I go 0.5 of tan of x, it's just flatter towards the middle, like so, okay? So, but if I didn't have tan x there, you couldn't really tell so much. I'll just zoom out a little bit so you can sort of see it. So if I did that, you couldn't really tell that I'd flattened out the graph. It's only when I put this on, the regular parent graph, you can see, oh yeah, it's been flattened out. Similar with this, to a lesser extent, not so much. The bigger the number is, the more it's exaggerated, of course. If I sort of go like this, it just looks like I have drawn my graph a little bit quickly, you know, whereas it probably looks more like the graph I've actually drawn. But if I compare it against tan x, you can see it's stretched out. So the vertical dilation is not so important for sketching. I'm not saying it's not important, it's just not important for sketching so much. The horizontal dilation is. Okay, so the first thing we should talk about is the period. So of the parent graph, so with sine and cosine, if you can remember, the parent graph of sine and cosine had a period of 2 pi. In other words, I'll just do it here just for a little drawing, that the graph repeats itself after 2 pi. That's its cycle, 4 pi, etc. And remember, it means any value here will be repeated 2 pi along. That's what it means. This value would be repeated 2 pi along. Okay, so just keep that in mind, that the period of sine and cosine is 2 pi. However, if you have a look at the graph that we've just drawn, can you see that the period of the parent graph, it actually repeats itself? So even if you just if you look between here and here, between the two asymptotes, there's a range of pi there. Okay, so the period for a tan graph is pi, not 2 pi. So it repeats itself every pi. So again, if I pick any old value here, to get to the same value on the graph, I only have to go over a distance of pi or a length of pi. And to get to that graphic, that point again, another length of pi, etc. So the period of the parent graph is pi. And I won't go through it in too much detail because we've done it for sine, but therefore for y equals tan bx, oops, period equals pi on b. Is that okay? So, again, I'll just use this as a scratch pad, and I'm going to pause the video, and I've been talking for so long, I'm just going to give you a quick bit of bookwork. So, for example, if I had, y equals 3 tan 6x, then the period would be pi on 6, just like that. That's all it means. Okay. So I'm going to pause the video. Okay, so period is pi on b, and so we've got an example up there which I'll erase now so it's gone, but y equals 3 tan 6x, the period is just pi on 6. Okay, so going to the next slide, I'll just rewrite the one bit of information we've got. So we've got period is equal to pi on b, like so. Asymptotes. Now, if you remember the parent graph, the asymptotes were always in the middle of the period, effectively. So the first asymptote what's wrong? You get used to it. Just make it just sound like as if you've got a bit of a cold. It's an asymptote. Yeah, asymptote. Okay, so that's how you do the P. The asymptote, it starts at half of pi on b. All right? So that means pi on 2b is the first asymptote. Okay, that's where I would label my first asymptote, at pi on 2b. So it's a periodic function, which means it repeats itself every whatever the period is. So we're going to have the same sort of thing happening here, in that the next asymptote is one period away, one cycle away. Now, in the textbook, you will find that there's a rather complicated looking expression there to describe the asymptote. If you want to read the textbook and you would much prefer to memorize 2k plus 1 times pi all over 2n, please feel free to. But the way I look at it is that the next asymptote are plus or minus pi and on b along. So I just paste them out according to the period. Okay, last thing I'll just talk about, and then I'll go through an example, and then I'll let you do practice. Reflections. Like sine and cosine, reflections are sort of fairly straightforward to think about. So with reflections, so y equals negative tan x is as expected. Flips over the x-axis, reflects, whatever, flips over. So if I just go to Desmos for a second, I'll be back to these notes in a moment. If I go to Desmos, so there's tan x in red, negative tan x, it just flips. Okay, so green, I'll get rid of red for a second. There we go. It's just goes from here down to negative pi and then through again, and then it just repeats over and over and over again. So it flips. So there's y equals tan x. that bit gets flipped that way, this bit gets flipped that way. So it's effectively just running down the other way. Now, in terms of y equals tan of negative x, okay, tan of negative x will effectively just give us negative tan of x because of the unit circle. You know, the tan of, if you assume x is an acute angle, then negative x would bring it down to quadrant 4, and therefore it would be a negative value. So it effectively works the same way. So if there's a negative anywhere, it'll just behave the same way. So if I go back to Desmos, I will come back to this screen, don't worry, but if I go back to Desmos, you will see that if I go y equals tan x, it's the same now. If I y equals negative tan x, there we go, it's exactly the same flip. Ironically, not ironically, but that means if I go y equals negative tan negative x, it's in fact the same as tan x, because those negatives kind of cancel each other out. So there's y equals tan of negative x. There's y equals negative tan x. You can see that they are both the same graph. Okay, so reflections really, whenever you see a negative either input, i.e. tan of negative x, or a negative output, i.e. negative tan of x, then you know it just flips. That's all. Okay, so let's go for a quick example, and then I'll let you go from there, I think, and have some practice time, and we will work with tan equations tomorrow. So let's have a look at this one here. This is from your textbook. Sorry, I'll just go into slide 11 there. So in your textbook, you've got question A will do. We've got y is equal to tan of 2x, and you've got x is, the domain for x is from negative pi to pi. So we're graphing from negative pi to pi. So in order to do this one, first of all, we identify the period. So the period is pi on 2. Okay, so pi over b. The asymptotes are at where? Well, first of all, I just halve pi on 2. So that's pi on 4. Then, within the domain that I'm given, I just keep on adding the period. So I go pi on 4 plus pi on 2. Well, that's 3 pi on 4. I won't do it for all of them, but I'll just do it for here. Right, that's all I'm doing. I'm just adding pi on 2. And then if I add another pi on 2, that'd be above pi, right? So I don't need to go any further. But I'll also subtract pi on 2 to see what else I can get. So if I subtract pi on 2 from pi on 4, I'd get negative pi on 4. And if I subtract another pi on 2, I'll get negative 3 pi on 4. Okay, so that's just adding or subtracting lots of pi on 2. Okay, until I've got all of the asymptotes within my domain. I know to stop when, if I add or subtract another period, I would get beyond the endpoints there. Okay, so that's all I need to do. Now I'll just draw it. So I grab my ruler out, draw away. Excuse me. I'm going to have it going from negative pi to pi. Good. I need to now look at sort of like the first asymptote, which is going to be, oh well, sorry, I'll do the zeros first. I split it in two like so. So we got pi on 2 here and pi on 2 here. oops, like so. And then I split them again for the asymptotes. Split them here. Might label them. Okay, so you work those out, but it's effectively, in terms of graphing, you're just splitting up the space again. So here's the domain, splitting up, split up, split up, and then you can go ahead and draw it. So we're going to have it sort of going, I mean, you can do it in one fluid motion if you think you're capable. I'm not very capable. I'm going to leave that one because it actually went through the origin like it's supposed to. But otherwise, you can sort of just do a sweep up that way and a sweep down that way. Sweep up that way and a sweep down that way, like so. But we do need to finish off here. So that wouldn't be good enough. I also need to do my sort of half sweep that way. Again, just following the pattern along. And then a sweep up that way. And I'm done. That's basically it. So that's question 2A done for you. Question B is a similar nature. C has a reflection in it. We've got 25 minutes, which is more than you'll need to do it, I think. But if you want to now have a go at exercise 14L question 2, I might finish off the lesson just by briefly talking about solving tan equations if we can. But I'll at least give you at least 10 minutes or 15 minutes to have a crack at that.